Our group name is Feedback 2.0. In our group is Kylie, RJ, Ian, and Ethan. And this is our presentation on drone troubleshooting in the pizza delivery sector, a comprehensive guide to the feedback control engineering behind fixing a delivery drone. The problem that this project is geared towards solving is to facilitate a drone flight that will deliver a pizza unharmed. Using what we learned throughout the semester in feedback, we did so as shown in this presentation. In order to have a realistic drone program, we had to prepare the drone for many possible things that could affect its typical flight. These include accelerating or decelerating too quickly based on responses in the program, the drone being affected by outside forces, such as wind, the drone having too much error in its GPS tracking and releasing the pizza at the wrong location for delivery, and the drone moving past a specified pizza release height, such as running into the ground or dropping from 10 feet off the ground.
So when modeling the initial system, there were a few assumptions that were made. When looking at the mass of the quadcopter, we referenced the DJI Matrix C100, which was the standard quadcopter weighing in at about 2.5 kilograms. And then when looking at the mass of a standard pizza in box, it was assumed to be about 1.5 kilograms, thus bringing the total mass of the system to right around 4 kilograms. Air resistance was then included into the model, and this was represented as a damping system. This damping system was given a value of 0.9, which was likely a pretty conservative value, but is the one that we ended up going with. And then the final components that were modeled were the input forces, both of the drone rotor as well as the force of gravity. And then these are seen on the left as FR for the force of the rotors and FG as the force of gravity. And then after constructing the drone system showed in the previous slide, we then constructed a circuit that was able to represent this using the impedance values of both the damping system and the mass system. This also displayed the overall force as a through force. Once this circuit was constructed, we then did circuit analysis to calculate the final transfer function. And upon completing those calculations, the final transfer function was considered to be 1 over the mass of the system times s squared plus the damping force times s. And then looking on to the next slide, the initial transfer function, once we had figured that out, we were able to implement that into an open loop model for the system. We're looking in the figure here, the transfer function from the previous calculations were included, and then you also see the two inputs, FR representing the force of the rotor and FG representing the force of gravity. So those were both included into the open loop system. And then lastly, once we had that open loop system, we were able to model it using MATLAB. So we had the transfer function, as mentioned back in slide 5, of 1 over ms squared plus bs, and then using 4 kilograms as a mass and 0.9 as the damping constant, we were then able to use MATLAB to plot the transfer function. Looking at the MATLAB plot here on the slide, it's pretty apparent that this initial open loop system is unstable. It seems to grow without bound, and so this was obviously a problem, and it was something that was going to be resolved in future iterations down the line. So.
The transient response of a system includes the rise time, settling time, and overshoot. For our system, we chose to analyze these 3 variables using MATLAB. At first, the open loop system had a rise time of 2.607 seconds and a settling time of 33.7 seconds. The overshoot for the system was 48.35, which is very large. Adding a controller to the system increased the rise time and decreased the overshoot significantly. After the addition of the PID controller, the rise time was 2.607 seconds, the settling time was 4.56 seconds, and the overshoot dropped to 13.26%. Being able to control the rise time and overshoot will significantly impact the pizza delivery. In order to ensure a successful pizza delivery, we decided to add these variables to our design specifications. For the second design specification, we chose to analyze the stability of our system. At the beginning, we realized we had a very large steady-state error. This is because when we originally applied unit step to the system, the amplitude of the oscillations grew larger and larger as time progressed. This is apparent in the graph in the right-hand corner. You can clearly see the amplitude growing exponentially over time. This is when we decided to add a controller and that it would benefit our system. After trying a proportional controller, we tried a proportional integrator and eventually a proportional derivative controller. But we determined that a PID controller would be best fit for the system to help control both the overshoot and steady-state error. The second graph on the bottom shows the step response after implementing a controller to the system.
Our system has two controllers. The first is contained in an inner feedback loop with the transfer function. This controller is a PI controller. This controller was chosen to mitigate any disturbances that would come between our transfer function and our other controller. The second is a PD controller. This controller was chosen for two reasons. The first is the proportionality control, which can be used to adjust the rise time of the system. The second is the derivative control, which will reduce any oscillations given by the input. We decided on the gain of our controllers through testing. Using MATLAB, we were able to test a large range of values easily. From our testing, we found that the ratio between Kp and Kd was important for controlling overshoot. It was determined that this ratio needed to be slightly less than 1. We also determined that in order to control our settling time, Kp had to be much larger than Ki. After adding our controllers to the Simulink and iterating, the final results for the system could be analyzed. From the step response plot, we can see that the settling time is about 4.6 seconds, and the overshoot is about 0.13. We can also observe that the system is stable. Looking at the Nyquist plot, -1 is non-circled and there are no unstable poles in our transfer function, so therefore the system is stable. As we can see from the Bodhi plot, there seems to be an asymptote at -180 degrees on the phase plot. This means that the gain margin will be infinite. The same can be observed from the Nyquist plot. The gain can grow, but the loop will remain fixed at 0 and will continue to grow off to the right of the plot. The same can be said about the phase margin. There's an asymptote at 0, so the phase margin will be infinite. The only way to destabilize the system would be to add a gain and a delay. For this reason, our system is very robust.